feel. Lay on the out and out, preach your words and verbs, and act academic sermons. Come along with me, take my hand and do some learning.
Welcome. Let's do some math. In this video, we're going to look at more of the fundamental properties of point set topology, and then we're going to introduce the idea of a manifold. So let's get started. As mentioned, we're going to look at core concepts in point set topology. Those are boiled down to the barest fundamentals: continuous maps, connectedness, and compactness. Continuous maps are exactly the types of maps we would want when we're trying to map one topological space to another, because they preserve the topological nature of the different objects. That is, if you have a topological property, it's going to be defined in terms of open sets, and continuous maps behave nicely with respect to open sets. Two of the most fundamental properties of topological spaces, whether you're looking at point set topology or just topology in general, is undoubtedly connectedness and compactness. The first thing topologists ask about pretty much any topological space: is it compact? Is it connected? So we won't get into compactness, but it is a very critical thing to understand if you want to do any sort of work in topology. So connectedness will be a property that's both easy to understand from the point of view of point set topology and something that we will have some focus on in these videos. When we look at manifolds, we'll look at the definition, and then we'll look at examples of one manifolds and two manifolds. So for starters, let's first look at these topological concepts with more depth. We left last time looking at open sets. Now let's talk more about open sets because they are very important for both looking at continuous maps and connectedness, and whenever you look at compactness, that will also be defined in terms of open sets. Say we have a set here, A, B, C, D. Say we define a topology on X, which is made up of these four sets: the empty set containing A, set containing AC, and X. You can check the properties of a topology and you'll find that all those properties are satisfied by this collection. The open sets of the topological space, X, together with the topology defined on it, tau, there are four open sets and they're exactly the things that are in this collection. So we just relist those elements. Let's say we change our set from X to R, where R is the real numbers. And then we change our topology from tau, which we had up here, to the empty set, the real numbers, so those are included in tau, along with all the unions of intervals of this form, where we have the interval from A to B, where A and B are both real numbers. All the unions. So examples of open sets that we would have in this topological space, which is often called the standard topology on R. One such thing would be, let's say U, that is just the union of this green interval and the red interval. If you take the union of these two intervals, that in total will be your open set. So everything we've put in yellow here, that itself is the open set. You could have infinite unions where there's an infinite number of gaps. Here we, in some sense, only have the one gap between them. And you can get any kind of set where you can construct it out of intervals. Notice if you take the intersection of any two intervals, you get the empty set or another interval. It's only when you take the union do you get things that are not intervals. The union of these two things is not another interval, but that's okay, because we said the unions of intervals. So U would be what we call an open set. Alternatively, let's say we define V to be this union of intervals where we can expand continually outward, approaching the limits of negative root 2 and 2. That would be another example of an open set. Now, one way to characterize an open set is to say, well, it's simply in the topology. That is, we look in the topology, boom, there it is, that's an open set. But sometimes it's not really clear what the open sets are. You can describe them given a set of criteria, but that criteria maybe won't explicitly show what these sets are. There's another way to characterize open sets, and it's using the following lemma. If you've got a topological space, we would say a set U, which is a subset of X, we would say it's open if and only if, for all the elements of U, there exists some open set V that contains X and is contained in U. Now, this is an if and only if statement. If we wanted to prove this, our proof strategy would require us to prove in two different directions. we prove an implication going from, let's say, left to right and then right to left. So first implication is, supposing a set is open in the way we usually define or think of open sets as just being in the topology, then we need to prove that it is the case that this follows. That would be one implication or conditional. Then we flip the arrow and we want to say, if we start with the cyan here, what we'll get, or what we can get by following logic, is this right here. If we prove both directions, we'll have proved this if and only if statement. So let's see if we can go ahead and do that. Our proof is going to require two implications. Let's first do the implication going from left to right. What we had to start with is that U is open. We have that to work with. So let's say we have an open set and we take an element of that open set that's arbitrary. By saying it's arbitrary, and as long as we don't use any specific conditions on X, we work with it in the general sense, we'll be able to prove it for all the things that are in U. Now what we can say is, well, simply, we observe that U, the set itself, we said it's open. That's what we have. It's a premise. It's our antecedent of the conditional, if you will. It's the thing we start with, and then we see what follows from there. So we have it to begin with. Of course, X is some element of U, and U is a subset of itself. So since X was arbitrarily chosen, we're always going to be able to find an open set that fits around X and inside of U. It's just U itself. So it kind of follows immediately that we have this implication. For the other direction, this will be just a slight bit harder, but not too much. What we start with is, if we have a set U and it has this following property, that for all the elements of it, there's some set, let's say Vx, that's open, such that it fits around X and inside of U. So that's what we have. That's our antecedent. That's the premise, if you will, what we have to start with. And now we want to see that from there follows that U is open in the traditional sense, that it's in the topology. We observe that you can take, for each X, there's some Vx. They could be different. They could be the same. There's some such element. If we take and we add them all up in the sense of taking the union and form U, U is going to be exactly equal to that union. Why is that true? Well, each of these Vx are contained in U by the property that we have, the antecedent property, or the premise, if you will. Each of them are contained in U. So you take the union of all of them, they're all contained in U, they're going to be collectively contained in U when you take the union. And it's going to include everything, because for each element X in U, you've got a Vx. So there's no element that you're missing. Therefore, U is equal to this. Now that means that U is going to be open. Why? Because each one of these Vx are open. And then we're taking U to be a union of open sets. By the definition of topology, part 3, any union of open sets is also open. Now we've shown that both directions of this biconditional, if and only if, hold. That means we've proven what we wanted to prove. Yay! Now this review of open sets was for the purpose of better understanding continuity, connectedness. First, let's look at continuity. When we look at a continuous function, what we're going to be doing is looking at a function between two topological spaces. Say we have those topological spaces, x and y with topologies tau of x and tau of y respectively. And let's say we have a function between them. At first blush, it's just some function between the set x and the set y. But the continuous part of being a continuous map is going to have to do with how tau x and tau y relate under this map. This is a different kind of structure preserving nature compared to what we looked at with group homomorphisms. That is, a continuous map in some sense respects the topology of these spaces, where a group homomorphism respected the group operations or structure. A function f is continuous if and only if the following is true. For any open set that you have in Y, well, remember, an open set simply means that it's an element of the topology. So for every open set in Y, the pre-image under F should be open in X. So open in Y, the codomain, means the pre-image in the domain is going to be also open. Now note, the pre-image may be a term that's not super familiar to you. What is that? Well, if you have a function, let's say from A to B, and C is some subset of the codomain, which is B, we would say the pre-image of C under the function G, it's simply this set. It's all the things in the domain such that when you map those elements under G, you get something in C. Let's look at a diagrammatic example just to make sure we have pre-image down. Supposing that we have two sets, A and B, and a function between them, where A is the domain and B is the codomain. And supposing we have a subset C, where C is a subset of B, we would say the pre-image of C under G is just the set of all things that map under G to something in C. And if we look back diagrammatically, maybe these four elements will each map to something in C. And if nothing else in A maps to C, we would just take those elements, and that would be our pre-image of C. The definition of continuity says that whenever you have something that's open in your codomain, that should imply that the pre-image is open in the domain. Now let's look at some specific examples with small topological spaces. Looking at the set X, which contains A, B, and C, and looking at a collection of subsets on it, as follows. This is a topological space taken together. Looking at this set with this topology on it and this topological space all together, say we define a map from X to A, which at first blush is just a set map, where we map the elements here to the elements here. And now we want to check, is this map F continuous? We look at the open sets in the codomain first. The empty set, the set containing 1, 3, and the set Y, they're all open in Y. They're open in Y because they're elements of the topology. And that's all of them. In each case, we look at the pre-image. The pre-image of the empty set under any map is going to be empty, because there's nothing in the empty set, so nothing can map to it. That's, of course, also open in X, because here it is. It's in the topology on X. If we look at the set 1, 3, the only thing that maps to an element in the set 1, 3 is C. C maps to 1. Now, nothing maps to 3, so we don't get anything from there, but we do pick up C because C maps to 1. Therefore, the pre-image is just the set containing C. In the domain space of X, we see that just this set containing C is not an open set because it's not in the topology. Therefore, it's not open in X. And it's true that here we have this is open and this is open. But in one case at least, we have an open set in Y, and that does not imply that the pre-image is open. Therefore, this function is not continuous. Let's look at another example, maybe one where it is continuous. Say we have the same X and the same Y with the same topologies, and we just change to a new map. G going from X to Y, that is defined like so. The same sets in Y are still open as they were before. If we look at the pre-image under G of these sets, the pre-image of the empty set is the empty set. The pre-image of the set containing 1, 3, it's AB because the things that go to 1, well, just A goes to 1. The things that go to 3, well, just B goes to 3. Nothing else goes to 1 or 3. Since the only things that go to 1 and 3 are A and B, we say we have the pre-image being A and B. And the things that go to something in Y, well, that's everything in X. Now, if we look and see which of these are open, the empty set is open in X because it's here. X is open in X because it's here. The set AB is open in X because it's here. Each one of these are open. So every instance where we had an open set in Y, that implied that the pre-image was also open. Therefore, by definition, G is continuous. Now, why are we talking about open sets? Why are we talking about a continuous function, which has to do with how open sets between spaces relate? Well, the fundamental topological properties are defined in terms of open sets. when you look at connectedness, compactness, when you look at things like the countability axioms and so on. Everything is defined in terms of an open set. If it's a topological property, it has to do with open sets. So that's why the maps between topological spaces should concern open sets and how they relate. Just like how group homomorphisms between groups should be concerned with how the operations change from one group to the other, so too with topological spaces should we be concerned how the open sets relate. Because what we want to track is how topological properties between topological spaces are maintained or not. One of the most important and simple topological properties is whether you are disconnected or connected. We say a topological space, X with tau, is disconnected if there exist non-empty open sets U and V such that they're disjoint, they don't overlap at all, they have no common intersection, and yet when you take their union, you get the entire parent space X. If there is such a pair, we say the topological space is disconnected. If there is no pair, then we say that the topological space is connected. So does the pair exist? Yes, then it's disconnected. If it doesn't exist, then it's called connected. Let's say we have two topological spaces. The first one y with tau of y, the second one x with tau of x. We want to ask ourselves, are these topological spaces connected? Yes or no? It's just one of them. Let's see. The first one I claim is disconnected, i.e. not connected, because if you take the set U and V as defined, where U is just the set containing 2 and V is the set containing 1 and 3, both of these are open sets and their intersection is empty, they have no common elements, and yet their union is the whole space, Y. That means that in some sense, Y can be split into two parts. It could be split into U and split into V, where both these parts are non-empty and they don't overlap. So in some sense, there's two pieces to this space. On the other hand, with X, I claim this is a connected set. The reason being is there is no pair UV like we had in the case with Y. Therefore, it's connected. It cannot be split into two different pieces in some sense. Now, ultimately, what being connected and disconnected amounts to, if we're actually looking at shapes, is whether it's in a single piece or more than one piece. That is, a shape like this is connected because there's only one piece. There are sort of these quote-unquote donut holes in it, but there's only one piece to it, where a disconnected space might look like this, where we have two different pieces to it. So when you hear connected, yes, formally, we're looking at whether there are two open, non-empty, disjoint sets that together their union is the whole space. But really, what it amounts to is whether we have more than one piece or whether we have just one piece. So if it helps you to think diagrammatically, think of connected in this way. This is connected, and this is split into more than one piece, so it's not connected. Now let's look at manifolds, a favorite topic of mine. We say that a topological space is an n-dimensional manifold if and only if X has the following properties. The first is that it's Hausdorff. We won't cover Hausdorff, don't worry about it. The second is it's second countable. We won't cover second countable, don't worry about it right now. The last is locally Euclidean. Do worry about that, and that is by far the most intuitive of these, and really the most important to quickly assessing what is happening with the manifold. To be locally Euclidean, what this means is that for every element in your space X, there's an open set, and since we said to be an n-dimensional manifold, we had to start with a topological space. Around X, we have an open set and a homeomorphism phi going from U to Rn. So here's where the n-dimensional comes into play, where this goes to Rn. And maybe I should have said locally Euclidean of dimension n. So the important thing here is that any element in your set, any point if you will, there's an open set and that set maps to Rn. Homeomorphism, take that for now to mean bijective, along with continuous, and finally continuous inverse. Most important, just as we survey this, is bijective and continuous. Let's look diagrammatically what it means to be locally Euclidean. If we have a manifold M of dimension n, that means around any point x, what we can do is find some open set U and a homeomorphism, or bijective continuous map with continuous inverse, to Rn. So it's like this set U is just like Rn, but maybe deformed a little bit. But in essence, in topological sense, U essentially is Rn. And this has to be true for all the points. So if we had a different point, let's say y, there would also be some other, let's say U1 or Uy, with another homeomorphism that goes to Rn. And when we say homeomorphism, what we're really meaning there is essentially that these open sets are like Rn. So around each point, it looks like Rn. It may be a deformed version of it, but it is essentially Rn. One of the most classic manifolds is the two-dimensional sphere. If we have a point x on that sphere, we can imagine mapping that open neighborhood or open set around x to R2. And really, this is a common experience that we all have. Since we live on the surface of the Earth, and discounting going up and down stairs and things like this, changing our elevation, a lot of the times we're simply just walking flat, and our lives are two-dimensional in terms of how we move. We're often moving forward, back, left, and right. We're in some sense moving on many copies of the plane, at least in a local sense. So locally Euclidean means that locally you look like Euclidean space. And if you go out onto a flat part of the Earth and you move around, you're essentially just moving forward, back, left, and right. So in a very simple sense, a two-sphere somewhat models the surface of the Earth, and the surface of the Earth is somewhat like R2 in any local patch. Also, by the way, Star Wars nerds, this totally looks like the Death Star. What's up? Now, we promised some other manifolds, and indeed, you can have all sorts of spheres of different dimension. A one-dimensional sphere is strictly just the circle. So you've already had much exposure to one-dimensional manifolds in math classes. Outside of math classes, you've seen two spheres all over the place. If you play basketball or soccer, you're going to see two spheres. You go on the beach and play with a beach ball, two spheres. If you've thrown a ball for your dog to retrieve, that's a two-sphere. There's many other two-dimensional manifolds. You could have a torus, which is essentially take your two-sphere and append on it this sort of arm here. It's extra kind of looping arm. And then you could have a two-sphere, but then you append on not one, but two looping arms. And you could have 3 looping arms, and 4 looping arms, and 5 looping arms, and 6 looping arms, and 7 looping arms, and 8 looping arms, and so on. As many looping arms as you like, and those are all different surfaces. But there are a class of surfaces called orientable surfaces. You could also have non-orientable surfaces that look like they self-intersect because we are putting them in 3-dimensional space and then projecting them onto this flat screen. But they wouldn't actually intersect if we were to embed them into 4 dimensions. But there's real projective space that's immersed, not embedded. There's the immersed Klein bottle, which you've perhaps seen before, that self-intersects because it's immersed into 3-dimensional space. You can't put it in 3-dimensional space and not have it self-intersect. But if you had another dimension, there's a chance that you could embed it in so it doesn't self-intersect, which is kind of trippy to think about. But here are just some examples of 2-dimensional manifolds or surfaces. But there are 3-dimensional manifolds and 4-dimensional manifolds and 5-dimensional manifolds, and it gets crazy. I hope you found this video useful. We'll see you in the next video.